Our first application of derivatives is actually finding absolute extrema of a graph. Remember, we've talked about the word extrema before. It just really means either a maximum or minimum value. And you can imagine this is pretty useful in real life. Anytime you're trying to find the maximum profit or minimum cost, you're actually finding absolute extrema. So all we mean by absolute versus local that we've talked about before is absolute is absolutely the highest or lowest that the graph gets, usually over a given interval. And there's all sorts of graphs out there. You can think of the cubic graph that goes upwards forever, kind of making an S-curve. It's not going to have an absolute minimum because it's going down forever. It's not going to have an absolute maximum because it's going up forever. So oftentimes, instead of talking about functions themselves, we're talking about just the specific interval of a function. So that's why we're just taking a look at an example here between the x values a to b. Okay, so you look at this graph, I should stand on the other side, but if you look at this graph, obviously over here, this point is giving us the absolute maximum over this interval. There are no parts of the graph that are higher than that specific point. Okay, so just be aware when we're talking about the actual maximum value or the minimum value, we're not talking about the x value where it occurs. We're talking about the y value. Okay, so if I know that this is the maximum value and it lines up with x equals a, to figure out what that y value here is, all we're doing is evaluating the function at a. And so in this particular instance, whatever the value of f of a is, we're not going to try to make up a number for that, but f of a is the absolute maximum of the function f over the interval from a to b. And notice this is important later on. We are including the a and the b in our interval. They are filled in dots here. And as a heads up later on, it's going to be crucial that we are including the endpoints here. If the endpoints are not included, that tends to be situations where there sometimes is not an absolute maximum or minimum value. We do want those endpoints to be included. And so this is the way that we would typically word it. And notice that as long as we're using function notation, this is giving us two pieces of information. We know that the actual maximum value is what you get when you plug a into f. But at the same time, knowing that the x value of a is where it's happening is an important piece of information as well. Okay, so if you're not writing it out in this format, so if we had just some sort of number here, you would want to probably expand on this just a little bit. And if you're not given that notation, you would say, say 13 is the absolute maximum. You would want to go ahead and expand on that and say that that occurs, I think I spelled occurs wrong, but it occurs at x equals a. And so there's kind of two different ideas there. We want to know what the actual absolute maximum is. We oftentimes want to know where it's actually happening. Okay, so if you take a look at the absolute minimum, it's the exact opposite sort of idea. Instead of looking for the highest point of the graph, we're looking for the lowest point of the graph. And here you can see that the lowest point of the graph, I didn't draw this terribly well, but it's about right here. Okay, so we're just going to have to make up a quick number or a variable here to represent this. But just to reinforce here, excuse me, the x value is where it occurs. I guess we'll just call it c. And the function value is the actual minimum value. And so there's not going to be a whole lot of difference of what I'm writing here, but f of c is the, oops, forgot the word absolute, is the absolute minimum over that same interval. And of course, if you wanted to expand on that and make sure it's absolutely clear to everybody that it occurs at x equals c. And so intuitively, this is not the most tricky idea in the world. But of course, in general, if we're doing this in real life, we're not going to have graphs sitting right in front of us. We're going to have functions that, like I mentioned earlier, maybe gives you the profit for a certain company, or maybe gives you the cost of shipping something, whatever it happens to be. So our goal here is to try to figure out, how do I get these absolute maximum or minimum values if I just have an equation? Okay, so let's just take a look at it a little bit closer here. Um, and we'll see that there's only really two categories of information that we can be working with here. If we're going to have something that's an absolute maximum, absolute minimum, it's going to have to either occur at one of the endpoints. Okay, it doesn't have to. So notice the maximum did occur at the endpoint, but the minimum value certainly was not the other endpoints. But the absolute extrema can happen at endpoints, and hopefully that makes sense because if you're taking a chunk of a graph, we can kind of imagine it going up like that and down like that forever. If you're taking a chunk of a graph, it's a pretty good chance that wherever you're chunking it out is going to be kind of out at the outer edge of what that function is doing. Okay, so you can have either of the endpoints generating an absolute extrema. The only other way that this can, the only other place that you can get an absolute extrema is at, you can see here, and this one isn't actually an absolute maximum. This one is the absolute minimum. But remember, this is something we talked about months ago. These are local minimums. I said the wrong thing when I was circling this. This would be a local maximum. So remember, top of the mountain, top of the hill, whatever you want to call it, is considered a local maximum. Bottom of a valley, bottom of a canyon, again, whatever you want to call it, that's considered to be a local minimum. Okay, so I think this probably makes sense that a local maximum could be an absolute maximum. All I'd have to do is make this hump go a little bit higher, and that would certainly be higher than the endpoint. That would become the absolute maximum. And you already see that this local minimum here is the absolute minimum as well. Okay, so this is something that we're not going to prove mathematically here, but hopefully it just makes sense intuitively that if you're going to have an absolute extrema, like we mentioned, it can either be the endpoints, but if it's not the endpoint, it has to be either local min or local maximum. Okay? It just doesn't make sense to have anything else happen. Okay, so really the end of the game here is to just mention that while we don't know how to find the endpoints using calculus, they're generally given to us. Right? If we're told where we're finding the absolute extrema between, we can just know that the endpoints or the x values of the endpoints are right here. Just evaluate the function to find the function values there. So we don't have to find those, but we can use calculus to figure out where the local minimums and local maximums are. And so we're going to have to expand on that just a little bit. Sorry for my ugly mug being right there next to the camera. But let's just kind of redraw a couple of things here and just make sure that we're on the same page in terms of finding the local maximum or minimum. What we're going to end up doing is, again, bring back some ideas that we had previously. So if I have your kind of standard, nice looking local maximum here, we've discussed how at the actual maximum value, that tangent line has to be horizontal, right? You can just take a board or whatnot and balance it right on top there. What's really happening though, keep in mind, is that you're kind of envisioning the tangent line as you get closer and closer. And that tangent line, I missed on that last one, becomes horizontal from either direction. And that's important, right? It has to kind of be approaching a horizontal line because, again, those tangent lines we are actually defined using limits, so it has to be happening from both the left-hand side and the right-hand side. Okay, so if we have a nice smooth graph where we have an absolute maximum, absolute minimum, sorry, I said the wrong word. It's right in front of me, so I said the wrong thing, sorry, but if we have a local maximum, that slope of the tangent line has to be 0. And as hopefully it's been drilled into your mind at this point, slope, when we're talking about something that's not a line, is always a derivative. Okay, so we know for a fact that if this type of local maximum is happening, then the derivative of, I guess I should have labeled this as x the way that I wrote here, but the derivative at that particular point absolutely has to be 0. And likewise, I'll just quickly draw it in here. If we had the same situation with the local minimum, we had the same thing going on. If I just kind of kept drawing in my tangent lines from either side, you would see that they converge to a horizontal line. Okay, so in either case here, the derivative has to be equal to 0. Okay, that's not the only thing that can be happening though. And so we've seen local minimums and maximums that look like that, but we've also seen local maximums or local minimums that are more of a V shape. And this one, remember, it's a little bit trickier. If something comes to a point, because let's just write this out. If this is, I guess we'll call this C this time. If I'm coming to a jagged edge, a point, whatever you want to call it, and this is not pointed, it's nice and smooth, but this is coming to a point. This is something where we've said in the past that derivative is undefined. And the reason for that is that if I look at the tangent line, trying to get to a tangent line at C coming from the left-hand side, this is already linear. So the tangent line is just the line itself. And as I approach the value of C, the tangent line is going to be going upward from left to right. If I try to approach from the other direction, then of course, same thing going on. The tangent line is the same thing as the line itself. But there's no gradual slope here to allow the tangent line to change. So there's no, trying to think how I want to word this, there's no uniform tangent line that these guys agree on. This one's always going up, this one's always going down from left to right. They don't agree. If the limits don't agree, they don't exist. So the derivative either doesn't exist or it's undefined, however you want to write that out. Okay, so really these are the two things that we're looking for when we're looking for our local maximums and local minimums. Now, that said, we did have some strange cases out there earlier that we're not really going to deal with here. Every function that we're going to be dealing with in this section is going to be continuous everywhere where it's defined. So we're not going to have to worry about the weird situations we saw before, where we have something like a piecewise function that looks like this. And that is something we discussed before, where this is technically a local maximum because it, excuse me, it is higher than all the points directly surrounding it. But the reason it's a local maximum has nothing to do with derivatives. It's just a jump in the graph. And this really doesn't happen in real life. And even if it did, we would just look at this. This would have to be a piecewise function. We've definitely talked about that before. So if we were working with a piecewise function, we would look at this as one of the endpoints anyway, right? Because the situation would be like this, right? You'd have the piecewise function, and you'd have something for x is less than, I guess just another letter here, and something else for x is greater than b. And that's what that would have to look like. I'm just trying to put in some variables so I don't have any actual numbers. And if you have a piecewise function that you're actually dealing with, which we're not going to in this class, it would literally spell out here, well, hey, b is another endpoint that we're going to have to test along the way. Okay, so that's the one that we're not going to deal with. I just wanted to address it since it came up earlier in class, that this is really nothing more than just an extension of what we said earlier. If you're given an endpoint, you got to check the endpoint. And so what this boils down to is that we can find local maximums or local minimums by applying this relationship. Okay, so the last thing that I have to be careful with and say here is that it doesn't work in both directions. If this is a local maximum, then the slope does have to be 0. If this is a local maximum, then the slope or the derivative has to be undefined. But just because I start with a derivative being 0 doesn't mean that this is going to actually end up being a local maximum. And so the one example, I think we've seen this before as well, is just your normal x cubed graph, your S curve here. If you look at the tangent line at a point right about here, that tangent line is back to being horizontal, and you can go from either direction if you want, but that is certainly not a local maximum or a local minimum. That goes back to being an inflection point. Just because the derivative of 0 doesn't necessarily mean it's an inflection point, but that's just the example here that we've had before. So I just want to make sure that it's clear going forward that just because we figure out where the derivative is 0 doesn't automatically give you one of the local maxes or minimums, but it gives you the points that are possible local maxes or minimums. And so we have to be a little bit careful as we go through these problems and realize that we have to figure out our possible local maximums or minimums based on finding the derivative and setting it equal to 0 or seeing where it's undefined. But then once we have our candidates, then we have to go through and figure out whether they are actual minimums or maximums. Okay? So we're almost to the point where we can put this all together and do a problem. But what we just discussed is a hugely important idea, so much so that these values where the derivatives are 0 or do not exist are called critical values. Sometimes you'll hear the word critical points. I want to make sure it's clear these are not points like on the graph, they're actually values. But all we're saying here is x equals c is a critical point. I just said critical point, but I should say critical value of the function f if there's actually two distinguishments here. We do want to make sure that c is an interior point of the domain, or for that matter, if you're working within a given interval, an interior point of the interval. Okay, so we stipulate this because from time to time you will get endpoints that have a derivative of 0. But we don't care about endpoints here. We're looking for a local maximum or minimum. And we've kind of talked about this before. If you've got a situation that does that, that's not really considered a local minimum or local maximum. I know it's higher than everything else, but it's not higher than everything else surrounding it because there's nothing over here. And so our textbook didn't talk about this, but I'm pretty sure we talked about this in class. This is called an endpoint maximum minimum. We're not trying to find those because we know where the endpoints are in our examples. So all we're saying is that C has to be an interior point. It cannot be right here. Right? That cannot be C because that's not interior to the domain. And I guess that word interior, just to specify that, just comes from the idea that if you're looking at this at, say, x equals a again, that would be your starting point of the domain, and maybe this goes on to infinity. So your domain there would be from a to infinity. An interior point just literally means something that's not the endpoint of your interval giving you the domain. And so you just have to avoid any points that happen to be on the edge of your domain. And then the second part is what we just discussed. So it's a critical value if it's an interior point of the domain and either the derivative at c is 0 or the derivative at c is undefined, or let's just use the phrase does not exist this time, because those are somewhat interchangeable in this idea. But that's what's going on. And so this is something that we have to check, but it's usually a quick check within the context of the problem. The hard work is going through and figuring out where the derivative is either 0 or where it does not exist. Okay, so so let's do a couple of examples about finding critical values, because that's the hard part. That's the part where you're actually doing the calculus. Once we've done that a couple of times, we'll just put it together and do one problem where we're finding the absolute maximum or absolute minimum, given some information. So let's start with this. Let's look at the function x divided by x squared plus 1. Okay, and maybe I should have written this down. I just said it, but we are just finding all the critical values. Okay, so just like anything else, there might just be one, there might be 2 or 3, there might be none. Okay, so when we say find all critical values, We're not trying to tell you there is more than one or anything like that. Just find everything that you possibly can. Okay, so keep in mind here that that first step said that our critical values need to be on the interior of the domain, meaning it can't be the endpoint of the domain. So in the back of our heads, we should quickly talk about what the domain of this expression is. Okay, so when we're working with a fraction, all we have to do is make sure that we're not dividing by zero, at least in this case, because we can certainly put anything we want in for x in the numerator. We can certainly put anything in for x in the denominator. We just have to make sure we're not dividing by zero. But the nice thing about this example, of course, x squared is positive. A positive number plus 1 is definitely positive. If it's positive, it can't be zero, so you're never dividing by zero. So the domain here is all real numbers, which means anything that we come up with has to be an interior point. Okay, so now the second step is nothing more than just take the derivative and then see where it's undefined or zero. So here, quotient rule, because we have a fraction, so we take the derivative of the numerator, which is 1, multiplied times the denominator, minus the derivative of the derivative of the denominator, which is 2x, multiplied times the numerator, and that should all be over the original denominator squared. Okay. And let's go ahead and simplify this a little bit, just because it's something we need to practice doing for certain things that we end up talking about a little bit later on in other sections. But really, you wouldn't have to simplify here. You can start to work it through what we know about fractions and figure out where the derivative is zero without doing the simplifying. But putting it together quickly, we would have 1 times x squared. Over here, we get minus 2x squared. So x squared minus 2x squared is going to give you a negative x squared. And then 1 times 1 is still 1. So make it look a little bit more nice in the numerator. Make it a little bit easier to work with. Okay, so now what we're asking ourselves is, when is this fraction equal to 0? Or when is this fraction undefined? Okay, so a fraction is only equal to 0 when its numerator is equal to 0. And it's only going to be undefined when its denominator is equal to 0. So anytime you end up with a fraction in your derivative, let me take that a step back. Anytime your derivative is one fraction, not just your fraction and something else, but if your derivative is just one fraction, all you're doing is literally setting both pieces equal to 0. So either negative x squared plus 1 is equal to 0, or the denominator x squared plus 1 squared is equal to 0. And you should probably be shaking your head at me right now saying, well, you just talked about how x squared plus 1 can never be 0. That means x squared plus 1 squared can never be 0. So this is going to have no solution. I wanted to write it out to make sure it's clear it's something we have to check, but there's nothing coming from that. So at no point is the derivative of this graph undefined. So all we're doing then is solving this last equation. There's lots of different ways you can solve this, but if you subtract 1 and then divide both sides by -1 to get x squared is equal to 1, you'll see pretty quickly that x is equal to positive or negative 1. Okay. And that's all we're doing right now. Right? We didn't say anything about trying to find the absolute maximum or absolute minimum here. We'll put that together later on. But basically what we're saying is, when we do that, the positive 1 and negative 1 are our two candidates for being absolute maximums or absolute minimums here. Okay, so I guess that does finish this particular example, but that's how it ties in. Is in the final example, when we go to find the, absolute maxes and mins, we're just going to find the critical values and then check the function values at the endpoints. Those critical values, whatever the highest one is, that's the absolute maximum. Whatever the lowest one, that's the absolute minimum. So that's our first example. In the next example, let's say we're working with, I guess we'll change the letter just to keep things straight if you're taking notes. Say we're looking at the cube root of x squared. Something that's a little bit weird to work with. You don't run into this too terribly often. But, excuse me, But same thing here, just think through the domain first. Really, there's two things going on. Squaring the x makes this positive, and working with nice positive numbers, you can always take the cube root of a positive number. For that matter, you can take the cube root of a negative number as well. So once again, the domain here is all real numbers. So as long as we find a, a derivative that's either equal to 0 or undefined, we're going to have a critical value. So in this case, recall that we don't really have a formula that we've memorized for cube roots. They're just not quite common enough. So anytime you run into any root that's other than a square root here, we typically go through and rewrite this as a rational exponent. So the rule for that is just get rid of your radical. Whatever the exponent was is the numerator of your fraction. Whatever the root was is the denominator of your fraction. And then once you have it written like this, you're just using the normal power rule to take the derivative. Okay, so the power rule says multiply by the exponent and then subtract 1 away from the exponent. So when we take 2/3 minus 1, 2/3 minus 3/3 is going to give you a negative 1/3. And then finally, as we've said before, probably rewrite this so that we don't have to deal with anything crazy like a negative exponent. So just a reminder here, if I try to rewrite this whole thing, I keep the 2/3 exactly as is. The negative in the exponent tells you that your x is moving to the denominator of your fraction. And then one last step here that's maybe not hugely necessary, but x to the 1/3 power, just to write it back in our normal cube root form, is the cube root of x. Okay. So that's what the derivative of the cube root of x squared looks like. And now we have that same scenario again. We have the derivative that's equal to a fraction. The only way that fraction is equal to 0 is if the numerator is equal to 0. It's undefined if the denominator is equal to 0. Okay. And you can see here that the point of this example is that not every derivative is going to be 0 to get a critical value. Of course, 2 is never going to be equal to 0, so that fraction is never equal to 0, but it's certainly going to be undefined when x is equal to 0. And technically, you're dividing both sides by 3, that's still a 0. Take up both sides of third power, you'll stick it at 0. So that's how you solve that, but that is your critical value here. Okay, so this is a little bit of a side note. It's not hugely important because we're done. That is our critical value. But if you were to graph this on your graphing calculator, this is one of those graphs that you don't see very often, but it basically looks like this. And kind of looks like the birds that at least I used to draw back in kindergarten. And so you have a nice smooth curve here, nice smooth curve here, but because of the nature of how squaring along with the cube root works right at the origin, this actually comes to a point. And that's why the derivative is not 0. It's not a nice smooth thing that we had before. It's coming to a jagged edge that makes the derivative undefined. Okay, so those are just two different examples of how we go through and find critical values. Of course, there's all sorts of other functions out there that you'd have to be able to deal with. Maybe you're working with natural log, maybe you're working with e to the x, or even some trig functions. But as long as you feel confident finding derivatives and solving equations that equal to 0, they all work the same way. Okay, so finally, let's put this all together and do an example. So this time we're going to be finding the absolute extrema let's say f of x is equal to e to the x minus 2x over the interval from 0 to 2. Okay. So as I mentioned earlier, you're almost always going to be given some sort of interval to be looking at, because oftentimes in real life, we end up with some sort of function giving you again, a profit function or whatnot. And in general, we're always going to assume that we're working with positive numbers. I shouldn't say always, but in a lot of cases, we're going to be assuming that we're working with positive numbers because that's just what happens in real life. So you'll almost always end up with some function that would do weird things if you're looking at negative numbers, but as long as you stay nice and positive, um, it's going to make a little bit more sense. So that's another reason why we're oftentimes given this set of endpoints. And so our goal here is, once again, two main steps. We're going to find the critical values, and then all we're doing after that is evaluating at the critical values and the endpoints. And I'll stop writing there because I know that everybody understands that once you evaluate those, all you're going to do is look for the largest one for the maximum, the smallest one for the minimum. Right? So, the endpoints are given to us. The evaluating at the endpoints is nothing more than a calculator problem or maybe a little bit of mental work depending on the numbers. Finding the critical values is where all the work is coming into play here. So to find the critical values, we're again taking the derivative. And here, nothing crazy like some of the other examples that we had to do, but it's relatively straightforward expression. The derivative of e to the x is itself. The derivative of 2x is 2. So I guess since it's a little less complicated, there's less to talk about here, but you can look at this and say that we don't have a fraction. E to the x is defined everywhere, so there is nowhere where this is undefined. You're not going to have a critical value coming from a part of your domain where the derivative is undefined this time, but we can certainly end up with 0 in this situation. Okay. So solve this, of course, add the 2 to both sides. And then there's different ways of thinking about this, but remember, to cancel out an e, we're always using natural log. So technically here, we're taking the natural log of both sides. The natural log and e are opposite, so they'll cancel out, and you're going to be left with x is equal to the natural log of 2. Okay. And in general, we like to be as exact as we can, so that's a usual way to leave your answer, but in case anybody was curious, the natural log of 2 is about 0.69. Not exactly, it's an irrational number, but it's about 0.69. Okay. And one of the reasons we actually want to take a look at that is for our critical value to matter, it needs to be in our interval. Okay, so if you don't have a general idea of what natural log of 2 is, put it in your calculator to make sure that it's in our interval. But if you know that natural log of 2 needs to fall in there regardless, then there's no reason to really write that out. Okay, so that was step 1. Step 2 is now just evaluating a function. Okay, so if we evaluate, just take it in order from smallest to largest, so we'll go to 0, then to the natural log of 2, then to 2. But if I evaluate f of 0, so we'll go ahead and write this one out. Anything to the 0th power is 1. 2 times 0 is 0, so we're going to be left with a 1 there. If we evaluate at the natural log of 2, then we would have e raised to the natural log of 2 minus 2 times the natural log of 2. And keep in mind again, just like over here, but the opposite direction, e and natural log are always going to cancel out. You're still left with the 2 that's remaining there, so this ends up being 2 minus 2 times the natural log of 2. And because we're comparing to see whether this is a maximum or minimum, that is definitely something we need to put into our calculator. You throw that into the calculator, and you're going to get about 0.61. Okay. And then finally, if I evaluate f of 2, you're going to end up with e squared minus 2 times 2. E squared is some sort of crazy number. 2 times 2 is 4 at least, but that's definitely another calculator problem. And that comes out to be almost exactly 3.4. Right? So now the easy part. Out of these three values that we got from evaluating the function, which one's the largest? Obviously, the 3.4 is bigger than the rest. That's going to be our maximum value. What's the smallest? The 0.61 here. So I'll write this out nicely in a second, but what we have here is our absolute maximum did come from one of the two endpoints. Our absolute minimum value, though, was not in an endpoint. It was actually the local minimum that was somewhere in between the two endpoints in our interval. So I'm just rewriting this mostly to make sure that we're clear about vocabulary and the way that we need to think through this. But we would say that the absolute maximum is about 3.4. Hopefully I'm still on the screen, okay? The absolute maximum is 3.4, and it occurs when x is equal to 2. And likewise, same description, we'll just change the numbers, but the absolute minimum is about 0.61. Is that what it was? Yeah, 0.61. And it occurs at, and this is where you can make a choice. You can put in your approximation, but in general, like I said earlier, you want to be as specific as you can be, as long as it's not an inconvenience. So you kind of want to know what the absolute minimum is as a value. You don't want to write 2 minus 2 times the natural log of 2, because that's really kind of tricky to evaluate. But because you might be doing some other things with this x value, because that's where the absolute minimum occurred, you should try to get the exact x value here. But just as a reminder from before, that is about 0.69. Okay. So that's the whole process. There's nothing really going on here beyond this. A lot of section 4.1 was here just to introduce the idea of critical values, because you run into working with those in a lot of different areas throughout the rest of chapter 4. Okay. So again, big picture, find the critical values by taking the derivative set equal to 0. Once you have the critical value, just compare the function value at the critical value along with the endpoints of your interval, compare them, and you're finished. So the only thing that makes any of these any more difficult is how tricky this expression is to take the derivative and how hard it is to solve. Okay, so I think maybe we should do one more. So partly I had another example made up in case we wanted to do it, and partly so just remember that there's one other detail that I need to throw out here. It's not really going to be used in our example, but this is something to also be aware of. Actually, a small detail along the way here, but if we're working with an open interval, meaning that the endpoints are not included, I just want to make sure that it's absolutely clear here that if you have an open graph like this, in this particular case at least, there is no absolute maximum or minimum. There's no absolute extrema here because the points are not included. And you cannot look at this and say, well, even though that's not included, maybe that point right there is the absolute maximum. Because remember, there's always room to squeeze another point in between the hole and the graph. So you can move just a smidgen over and get a little bit higher. And so again, I said this earlier, but we didn't have a good visualization here, is that if you have open endpoints, you don't have to have an absolute maximum or an absolute minimum. That's why we've been working with our filled in endpoints with all the examples that we've done so far. Okay, that said, excuse me, even if you are working with open endpoints, you can have a maximum or minimum value. Okay, so here we're not getting the absolute max or min from the endpoints. There is no absolute maximum here because this point is, well, little tiny point here is higher than this other point off to the left. And there's, again, room for you to move closer and closer to that open endpoint. Put this down here. That would give you the absolute minimum. So again, the absolute minimum is not a point. That's why I worded it weirdly here. but you can still have an absolute minimum or absolute maximum even though you don't have the endpoint. So it is still possible. And so I just wanted to kind of rehash why we had been working with the closed interval and the closed points. But the last theorem that shows up here is something that we don't necessarily say out loud and use later on, but it's a nice thing to know, is that if there is exactly one local extrema in the interval, then that point must also give either an absolute maximum or minimum. Okay. So the crucial part, it's kind of emphasized on its own here, is just the exactly one. If there's exactly one local extrema on the interval, then that point has to be, the y value of that point has to be either an absolute maximum or an absolute minimum. And what it really boils down to is if this local extrema was a local maximum, then it's going to be an absolute maximum. If it was a local minimum, it's going to end up being an absolute minimum. But I had to use the word extrema up here because it's important we have exactly one. Okay, we cannot have a local max and a local min and have this work out. It has to be just a local max or a local min, not more than one. And of course, you can draw these. I'm going to purposely draw them with the open endpoints here. If I'm drawing something so that there's exactly one local maximum in between them, I have to be going up and then coming back down. If there's only one, that's the only way that we can do it. And that's very clearly an absolute maximum value. And if I tried to, excuse me, if I tried to draw something where this local maximum was not the absolute maximum, then the only way to do that would be to come back. Sorry, shouldn't have drawn it like that. The only way to do that is if you say, well, hey, here's a local maximum that's not the, excuse me, not the absolute maximum. That means the other endpoint or some other points have to be higher. You've already gone down though. If you've already gone down, you're gonna have to come back up. And guess what? Now I've got two local extrema here. Okay? And no matter how you try to mess around with this, if you have jagged edges or anything like that, you're still gonna come to the same conclusion that you end up, excuse me, with more than one local extrema if you're trying to get to something that's breaks this theorem. And so more or less, the moral of the story here is if it doesn't matter what your endpoints are doing, if you just have one local minimum or one local maximum, so I just did a local maximum, so just to be clear here, I have one local minimum, it's got to be the absolute minimum as well. Okay, so that can be useful if you're working with larger problems. Let's actually, I'm going to stop here. I was thinking about doing another example, but I think that's just a little bit too much for right now. So if you guys have questions, let me know, and I'll post another example here. But I guess what I was going to start to say is later on when we do some actual applications that utilize the information from section 4.1, it's nice to know if there's exactly one local extrema that it has to be the absolute, because there are certain circumstances where it's going to be very difficult to either find or evaluate at the endpoints. Right, so I apologize. I kind of rambled on at the end here because it slipped my mind to write this in my notes until I was going through it and realized I had never said this. Like I said, if you have any questions at all, let me know, and I'll try to make another better video.